Chapter 5 is an introduction to solutions and aqueous reactions. Some of these quotes I think are pretty interesting. Other ones I just kind of ignore. But I like this one. Science may be described as the art of systematic oversimplification, the art of discerning what we may with advantage omit. And that's very, very true in Chem 1A. There are a lot of pesky little details that we can just ignore, and then we can look at the big picture much more efficiently. There's a first section. This is 5.2. There is a 5.1. I don't remember what's in it. Apparently I didn't think it was worth lecturing on. So read that. I'm sure it's interesting, but I'm not going to test you on it. So solution concentration. Chemical reactions involving things dissolved in water are very, very common and very important. And so we need to talk about reactions that occur in solutions. And first of all, we have to talk about, well, what is a solution? So a solution is a homogeneous mixture of two substances. Homogeneous, remember, is uniform throughout the mixture. It doesn't have different segments or lumps or anything. It's just uniformly mixed. There are two parts to a solution. There's the solvent and the solute. So the solvent is generally the part that there's more of. In an aqueous solution, the water is the solvent. By definition, aqueous is dissolved in water. So the solvent is the thing that there's more of, and the solute is what's mixed into the solvent. So you could have one solute, or you could have two solutes, or you could have 100 solutes. But these are all dissolved in the solvent. This is a mixture, not a compound, and so the amount of solute is variable. Like salt and water, you can put a little bit of salt in a cup of water and you make a solution, a saltwater solution. You could add more salt. It's still a saltwater solution, but now it has more salt in it, right? So these are mixtures. We have different ways of describing solutions, qualitative descriptions and quantitative. Qualitatively, we talk about dilute and concentrated. A dilute solution is going to have a small amount of solute compared to the solvent. A concentrated solution is going to have a large amount of solute compared to the solvent. And these words, concentrated and dilute, are used the same way we use them in regular life. Like you go to the store and you buy orange juice, concentrate in a little can. It's frozen, right? So can you just thaw that out and drink it? Not really, right? It is way too concentrated, right? So you pour it in a pitcher and you add water and you dilute it, right? Until it's the right strength and it's more like fresh squeezed orange juice. You can also buy concentrated cleaning solutions. You can buy the spray bottle and then you can buy the refill, and you take the refill bottle and you just put a little bit in the spray bottle and then you add a bunch of water. You take the concentrated solution and you dilute it, right? So we're talking about the same thing here. Of course, qualitative descriptions like that are only somewhat useful. We often need to know, well, exactly how much stuff is in this solution. And so there are several different units we use to express concentrations quantitatively. And a very common way in chemistry is molarity. This is abbreviated capital M. Molarity is defined as the amount of solute in moles divided by the volume of the entire solution in liters. It's important to note here is the volume of solution. It's not the volume of the solvent. And so this is an important definition to know. Molarity is the amount of solute in moles divided by the volume of solution in liters. And yes, you do have to use those particular units, moles and liters. So here's an illustration showing how we might prepare a solution with a specific concentration. And you're going to need to do this on Thursday. In the lab, you're going to make a solution of sodium chloride in water. So here what we're doing is we're trying to make a 1 molar solution. So 1 molar means that there's 1 mole of sodium chloride per 1 liter of solution. So we're making this in a 1 liter volumetric flask. 1 liter is kind of big. We have some 1 liter flasks over there. So if we want a 1 molar solution, we're making 1 liter of solution, we need to put 1 mole of sodium chloride in here. So we measure out 1 mole of sodium chloride. We do that by figuring out the mass that's needed and weighing it on a balance, so 58.44 grams of sodium chloride. We need to get all of what we weighed out into the flask, and that's one of those things that sounds easy, but it actually is a little trickier than it seems. You need to get all of it into the flask and not leave any in the container you weighed it. Then you need to add water. A volumetric flask has a line on it. Here, I think the line is up here. Oh yeah, it's pointed out right here. It has a line on the neck. The reason that this flask has a long, skinny neck is because when the diameter of the opening is small, then a small change in volume will give you a noticeable rise in the level of the liquid. So by having this neck be narrow, it allows us to measure more precisely the volume of the solution. But that makes it hard to mix the solution. So what we want to do is we want to add water and not fill up the fat part down here, only fill it up partially, so that we can shake it and agitate it and get all of that salt to dissolve. After we get the salt dissolved, then we want to finish filling this up. And we're going to look at the mark on the neck, and the mark could be anywhere here. It just depends on how the glass was blown. They mark it afterwards. You fill it up to the mark so the bottom of the meniscus is at that line. And then you would need to stopper this. Some flasks use a plastic cap that snaps on. The ones we have use ground glass stoppers. And so you put the stopper in there to keep the water from, solution from coming out, and you turn it upside down. And when you turn it upside down, this air bubble will go up the neck and into here. And then you turn it right side up again, and that's 1. And in the lab, I think it tells you need to do that 20 times to thoroughly mix it and get it uniform. Any questions? So this doesn't require a calculator. How many moles of solute are required to make 3 liters of a 2 molar solution? 6. What does 2 molar mean? 2 moles per liter. So for every liter I need 2 moles, and I'm going to have 3 moles. Whoops. Oh, I didn't get the animation on that one. So it's 6. Oh my. Let's try that again. There we go, 6. Any questions? So this one asks us to calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. This is asking us to calculate the molarity. So we need to use the equation for molarity. Molarity equals moles of solute divided by liters of solution. What's the solute here? Sodium nitrate. Well, do we know how many moles of sodium nitrate we have? No, but could we figure it out? Sure. So they gave us a mass. So 45.4 grams of sodium nitrate. We can convert that to moles of sodium nitrate by using the molar mass. And so we have to calculate the molar mass. So we look at the formula. There's 1 mole of sodium and 1 mole of nitrogen and 3 moles of oxygen. We're getting 85. And here's a sig fig question. How many significant figures does that have? It looks exact. As it's written, it has 2, but it should have 4, right? Because the molar masses of the elements that I used all had 4 significant figures. So this should have 4 significant figures. What do? Add some zeros. So this is 85.00 grams is equal to 1 mole.
And that's because the masses on the periodic table are estimates?
The masses on the periodic table are measurements, and no measurement is exact. It's a little hard to get our minds around sometimes, but you can't measure anything exactly, because you think about, well, if you zoomed in further and further and further and further, is it exactly on that line? Is it exactly 1 inch? It might be as close to 1 inch as we can tell with our eyes, but is it exactly? No, we can't say that.
Then why is 2.54 exact?
That's an excellent question. Then why is 2.54 exact? How is 1 inch exactly 2.54 centimeters? They made it that way. They defined it that way. So why is a foot exactly 12 inches? Because we made it that way, right? So we said the units are related to each other in this way. The relationships between the units are exact, but when we measure something, there's not exact. Okay? So it is tempting when we come up with a whole number. It's like when you go to the grocery store and it comes out to be $100, and you're like, ooh, maybe I should go buy a lottery ticket or something, right? Because it's like, how you couldn't do that if you tried, right? But here it just comes out to be even, 85. Doesn't mean it's exact. So that was kind of an aside thing that I get off on all the time. Weird tangents. So 1 mole, 85.00 grams. We see that the grams cancel out. 45.4 divided by 85. And my calculator's giving me a mess of numbers. But I look at what I've got here, and this had 3 sig figs, and this had 4. So this number should have 3 significant figures. So there's my 3rd significant figure. I don't want to round this yet, though, because I'm going to use it in a calculation. It's always a good idea to write down 2 extra digits before you stop. And so then I can plug this in up here. This is 0.53411 moles divided by, what's the volume? 2.50 liters. And how many significant figures should this answer have? 3. 3 is a good guess. Like if you're just completely guessing, always guess 3. It's right more often than not, because of how they do the problems. So 3 significant figures is a 2, 1, 3. I'm going to write down 2 extra digits because that's what I do. Moles per liter. And then I'm going to round this, and my final answer is 0.214. And I can write this as moles per liter or 0.214 capital M. It has to be a capital M because a lowercase m is meters, right? Capital M also means mega, but only if it's in front of another unit. Got so many M's. There's a lot of K's also. Any questions? Capital M is an abbreviation for this abbreviation. 0.214. So molarity is a very useful conversion factor. Molarity works a lot like the molar mass and allows us to convert moles and liters of solution.
When you write the molarity, do you have to write what the solute is?
That's a good question. When you write molarity, do you have to write what the solute is? Sometimes it's important and sometimes it isn't. It depends on the problem. So in this problem, we were only talking about one solute, sorry. The only one mentioned was sodium nitrate. If you had a problem where it was talking about a bunch of different ones, then it might be important to specify which one you're talking about. It's a good question. So molarity is a conversion factor, just like molar mass. So an example of using that, here we have a 0.5 molar solution. So when you read that, capital M, you read molar, it's nothing to do with teeth. That contains 0.5 moles for every liter of solution. So we use capital M as the abbreviation for molarity, and it's shorter to write, and it's nicer on a computer because you don't have to do moles / liters or worry about a fraction or anything. But students often forget what the capital M stands for. So it's going to show you something like this in the problem, and what you should do is when you first write it down, translate that capital M into moles per liter. So when you see 0.500 molar sodium chloride, don't write that down, write down 0.500 moles of sodium chloride per liter. And now we see, oh, that's a fraction, right? And this allows us, if we have liters of solution, we can calculate the moles of sodium chloride. Or if we have moles of sodium chloride, we can calculate the volume of the solution. So this is the relationship between volume of solution and moles of solute. So how many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? Well, let's write down the numbers. I have 1.55 liters of solution, right? And 0.758 capital M, which is moles per liter. So this is moles per liter. You might as well just make that a whole big fraction. Moles of what? Sucrose. Per liter of solution. We often abbreviate solution like that. Okay, so that's the information I was given. And then one of those is going to be my starting point, and the other is probably going to be a conversion factor. What am I trying to find? Grams of sucrose. So again, this is really just a dimensional analysis problem, but we're just adding new units, right? So I'm trying to find grams of sucrose, and I need to decide which one of these is my starting point. This one could be used as a conversion factor, right? Moles per liters. This one, the volume of solution, can't be used as a conversion factor. It's just an amount. So this is the one I'm starting with. Let's see, I'll just highlight that. That's the one I'm starting with. That's my starting point, and I'm going to try to figure out how I can get from liters of solution to grams of sucrose. Well, they gave me this. I probably need to use that. This relates liters of solution to moles of sucrose. So I can take liters of solution and calculate the moles of sucrose in that. Can I go from moles to grams of sucrose? Yeah. Molar mass. They gave me the formula for it here so I can calculate the molar mass. Any questions about the path? At least one person looks very concerned. So I've got my path. Now I'm just going to follow my path. So 1.55 liters of solution, and I'm going to convert that to moles of sucrose. And then to grams of sucrose. Just following the path. Liters of solution, moles of sucrose, grams of sucrose. Liters, moles, grams. Liter of solution comes down here, so that unit cancels out. Moles of sucrose comes down here, so that cancels out. So this middle term is moles and liters, and that's where my molarity gets used. So yeah, 0.758 moles of sucrose. So 0.758 moles of sucrose per 1 liter of solution. Sometimes it gets used upside down and you put liters on top and the moles on the bottom. But if you just make a path and follow the path, you don't even have to think about it. It'll take care of itself. And then here, we need the relationship between grams and moles, and that's going to be the molar mass of this compound, which we have to calculate. But they gave us the formula. So there are 12 carbons times the mass of a mole of carbon, and there's 22 hydrogens times the mass of a mole of hydrogen, and 11 oxygens times the mass of a mole of oxygen. And we can tell this is going to be kind of a big number. My calculator is giving me 342.296. And that's the mass in grams of 1 mole of this compound. Now that really should only have 4 significant figures, but if I look up here, this is 3 sig figs, 3 sig figs. If I write extras there, it's not going to hurt anything. It's always better to carry extra digits. So I need to take 1.55 times 0.758 times 342.296. I should have 3 sig figs, so I'm going to write down my 3 and then a couple extras. Grams of sucrose. And then for my final answer, I'll round that to 402 grams. Any questions? This is a very, very important type of calculation in chemistry. Because if we want a solution, like if we wanted to make this solution 1.55 liters with this concentration, this is how we would figure out what mass of sucrose to weigh out, right? And then we dilute it to a volume of 1.55 liters. So we don't need a calculator for this one. If we dissolve 25 grams of salt in 251 grams of water, what's the mass of the resulting solution? 276. So we don't want to overthink this, right? So we've got some salt, weighs this. We have some water, it weighs that. You put them in the same container, what does the contents weigh? It's just the sum of those two, right? So 251 plus 25, 276. Any questions? So we often store solutions as in concentrated form. Just like you go to the store and you buy concentrated cleaning solutions or concentrated orange juice. It saves space, it's more efficient for shipping, all kinds of stuff like that. So we refer to these solutions as stock solutions because we keep them in stock in the stock room, right? So they're stock solutions. But we usually need something that's more dilute, and so we take the stock solution and we dilute it to make the concentration that we need. When you dilute a solution, the amount of solute doesn't change, only the volume of the solution changes. So this is like when you're making orange juice from frozen concentrate, right? You can imagine this with me, picture it in your mind. You got that can of orange goodness, right? And you squish that and you get all of it to go into the pitcher. And then you add 3 cans of water to it. Does that change how much orange goodness is in the pitcher? No. It's all still in there. The difference now is that it's got more water in it, but the moles of stuff is the same. So if we take the molarity of the first solution, moles per liter for the first solution, times the volume in liters of the first solution, that gives us moles. And that will be equal to the molarity times the volume of the second solution. The molarity is going down, the volume is going up when we dilute it, but the number of moles are the same. So the moles before and after are equal. Looks like that equal sign got subscripted. So here's an illustration showing the preparation of a solution from a stock solution. And we're going to be doing this on Thursday as well. So here the task is to prepare 3 liters of 0.5 molar calcium chloride from a 10 molar stock solution. So we have a 10 molar stock solution available. We want to make 3 liters of 0.5 molar solution. So we want 3 liters of 0.500 moles per liter. How many moles of calcium chloride do I need? Three liters times 0.5 moles per liter. 1.50, well, actually 1.5 moles, right? And then I'm going to take the 1.5 moles and divide it by, wait a minute. I'm doing this the other way, and so I just confused myself. That's how many moles we want, and we're going to get it from this 10 molar solution. So we need 1.5 moles of solute. I want to know how many liters of solution to use, and the concentration is 10 moles per liter. 10 moles per liter. So 0.15 liters. So that's kind of thinking it through, but what we typically do is we use this equation. M1V1 equals M2V2. The molarity of the first solution times the volume of the first solution is equal to the molarity of the second solution times its volume. One of these will be unknown, and we'll have information for the other 3, and so we can just rearrange the equation and solve for that. So in order to prepare this volume of that solution from this solution, I need to know what volume to measure out. So I could call this the volume of the first solution. This is the molarity of the first solution. This is the molarity of the second solution. So I'm trying to find V2. So I'm going to divide both sides by M2. So to find out how much of the stock solution I need to use, I have M1, 0.500 moles per liter times 3 liters. Oh, that's why I had the wrong number of sig figs. I left off a 0 there. Divided by 10.0 moles per liter.
So that's also calcium chloride, 10 moles.
Yes. So the 10 moles per liter stock solution has 10 moles of calcium chloride for every liter of solution. And I want a solution that's only 0.5 moles per liter. So I need to add a bunch of water to it. But the solute is the same. And so if we do the math here, 0.5 times 3 divided by 10, we get the same answer, 0.150 liters. We're going to measure out 0.150 liters of our concentrated solution and put it into a container. This is a 3-liter flask because that's the volume we wanted to make. And then we're going to add water until the solution reaches that volume. Any questions? The 1s and the 2s here do not necessarily correspond to the concentrated and the dilute. You just need to match them together. So I could call this volume 2 and concentration 2 if I wanted, but those go together. They both need to have the same number, and this is the other one. So to what volume in milliliters should you dilute 100 milliliters of 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? So here we have the word dilute. This is a dilution problem. So we're going to use M1V1 equals M2V2. So I'm going to take the numbers out and identify what they are. So I've got 100.0 milliliters, and I have 5.00 molar, so that's moles per liter. It's moles of calcium chloride. And I have 0.750, that's not a 5, moles per liter. That's also calcium chloride. Well, this first one is obviously a volume, right? So I'm going to call that V1. And then this is a molarity, so I'm going to call that M. And I'm going to call this other one's a molarity. I'm going to call that M. Which one of these goes with the 100 milliliters? The first one, 100 milliliters of 5 molar. Those go together, so that's V1 and M1. So then this other concentration is going to be M2, the other one. And we're trying to find a volume. So we're trying to find volume 2. So we have, in this equation, there are 4 variables. I have, bless you, 3 of those and 1's missing. So I take my equation, M1V1 equals M2V2. And I'm solving for V2. So I'm going to divide by M2 on both sides. V2 equals M1V1 over M2. So now I'm going to put things in. Molarity 1 is 5.00 moles per liter, and volume 1 is 100 milliliters.
Would it convert it before?
Yeah, do we need to convert it? Let's wait and see. Sometimes we do, sometimes we don't. Molarity 2 is 0.750 moles per liter. So what happens with the units here? They cancel out, right? I have moles per liter in the numerator, moles per liter in the denominator, those cancel out. And I'm left with milliliters, which is actually the unit that I was asked to find. So here it's better not to convert. So 5 times 100 divided by 0.75. Volume 2 equals, my calculator is giving me a lot of 6s. How many sig figs is my answer going to have? 3. So I'm going to call this 667 milliliters, and we just escaped the sign of the devil. I don't know why they picked that one, but any questions? Mm-hmm.
So you're measuring that out like in the flask or whatever, and that's rounded, so it doesn't need to be like that exact to get.
Yeah, so that's a good question. When we think about making this practically, right? So 667 milliliters, could we measure volume more precisely? Yeah, we could. But we're trying to get a 0.750 moles per liter solution. We don't need more precision than that. So we're not going to knock ourselves out on the rest of this. You know, when it says approximately 5 milliliters, just eyeball it. If it says 5.00, then you measure it carefully. Okay, so here we just need to get that volume to the nearest 1 milliliter. And this volume, though, needs to be to the nearest 10th because of where it ends up going. But this initial concentration is only 3 sig figs. So, any other questions? So you'd take 100 milliliters of the concentrated solution and you would add water until the total volume is 667 milliliters.